Hi folks, great to see you. Quick question, how much does the size of your telescope's aperture really matter? Is bigger always better? I get these questions a lot, so in this video we're diving deep into aperture. What it is, why it is crucial, and how it relates to things like light gathering power, limiting magnitude, and resolving detail. I'll also show some real-world examples from my own astrophotography sessions with different telescopes, and I'll show you some free tools you can use to better understand how your telescope's aperture may affect your stargazing experience or astrophotography. If you stick around until the end of the video, I will help you decide whether a bigger aperture telescope is worth your investment and when it is not. I'm Wido, I'm an astrophotographer from Utrecht, the Netherlands, and you are watching Wido's Astroforum. So, what is aperture? A telescope's aperture refers to the size of the lens or mirror the telescope uses to collect light. It is often expressed as the diameter of the telescope's lens or mirror. Over the years, I've actually come to believe that this is the heart of your telescope. Why? Because the bigger the aperture, the more light your telescope can collect, and more light means you can see fainter objects and capture more detail, whether you're stargazing or doing astrophotography. Or, as Queen already put it in Bohemian Rhapsody, a bigger aperture helps you to open your eyes, look up to the skies and see. So think of aperture like buckets in the rain. A small bucket will collect some water, but a large bucket will collect a lot more. Telescopes do the same, but with light. Just don't leave your telescope out in the actual rain like I might have done once or twice. Now, for a lot of folks, it gets confusing when telescope enthusiasts start talking about things like light gathering power, limiting magnitude, and resolving power, which are all directly tied to the aperture of your telescope. So let me break them down for you so you better understand what all of this means, starting with light gathering power. You probably noticed that most telescope mirrors and lenses are actually round, except for the funky hexagonal designs like the James Webb Space Telescope. As such, light gathering power is calculated by using the surface area of a circle, so that's pi times the radius squared. You might remember this from high school. Here's the formula. Let's do some calculations, shall we? A 50mm diameter telescope like the C-Star S50 you see behind me has a radius of 25mm. Square that and multiply it by pi, so that's 3.141592, etc. And you get to about 1964. That number alone isn't super helpful until you compare it with another telescope. For example, let's also take a 100mm aperture telescope. So that's 2 times the diameter. Using the same formula gets you to about 7,854. When you divide that by 1964 of the 50mm aperture telescope, you will see that 100mm aperture telescope collects 4 times more light than the 50mm one. Alright, so if you want a shortcut, just divide the larger aperture by the smaller one and then square the outcome. So 100 divided by 50 will get you to 2 squared, which equals 4. It gets really interesting when we compare a 200mm aperture telescope, like my Celestron Edge HD 8-inch, to a 50mm one. It will get you to 4 squared or 16. So the 200mm telescope has a 4 times bigger diameter, but it actually gathers 16 times more light. And that is actually very important to understand. The light gain you get with a bigger aperture is exponential. And hey, if you're not a fan of math, don't worry. I've included some easy-to-use calculators on my blog that do the math for you. You will find the link in the video description below. So, how does aperture actually help you to observe or photograph objects in space? Well, first you need to understand how bright or dim those objects in space actually are. Well, this goes way back to ancient astronomers like Claudius Ptolemy, who ranked the stars from a first magnitude, which was the brightest star he could detect with the naked eye, to a sixth magnitude, the faintest star visible to the naked eye. Then in 1856, an English astronomer called Norman Pogson turned this into a logarithmic scale to calculate differences in brightness between objects in space that we still use today. Here's the formula. So what the formula tells us is that a 6th magnitude star is about 100 times dimmer than a 1st magnitude star as calculated by 2.512 to the 5th power. And that's the difference between the magnitude 6 and magnitude 1 star. By the same formula, an 11th magnitude star is around 10,000 times dimmer than a 1st magnitude star. So you will notice that some of the brightest objects have a negative magnitude. That's just because they are so bright they go beyond the original scale. Just remember, the lower the number, including the negative ones, the brighter the object appears in the sky. Let's do a little comparison. So the sun is at minus 26.7, and be sure to use some serious solar filters before pointing your telescope at the sun. The full moon is minus 12.7, and Venus and Jupiter can shine at minus 4.7 and minus 2.9 when they are closest to Earth. If we look at Sirius, which is the brightest star in our night sky, it is at minus 1.46. Now, when we use the brightness ratio, it turns out that Sirius shines 13 billion times dimmer than our own star, the Sun. However, if we would place Sirius next to our Sun, it would actually shine 25 times brighter. But Sirius is 8.6 light years away, so that's over 80 trillion kilometers or 50 trillion miles. So let's also look at deep sky objects like galaxies and nebulae, which are much dimmer. For example, the Andromeda Galaxy, our neighboring galaxy, is a magnitude 3.4, and the famous Orion Nebula is a magnitude 4, and both are still visible to the naked eye. The Eagle Nebula is a magnitude 6.4, and you would usually need a telescope to spot it. M101, the Pinwheel Galaxy, is at 7.9, M51, the Whirlpool Galaxy, at 8.5, and the Horsehead Nebula is actually a dark nebula and has an extremely faint magnitude 9. If you want to play around with brightness comparisons, there's a free calculator in my blog. Links in the description below. Now that you know how apparent magnitude works, let's talk about something you'll often see in telescope specifications called limiting magnitude. This tells you the faintest object the telescope can still detect, and it depends entirely on one thing: the aperture of your telescope. So here's the formula. According to this formula, your limiting magnitude is about 10.5 with a 50mm aperture. That's already good enough to see some of those faint objects I just talked about. But if you're using a 200mm aperture telescope like an 8-inch reflector, that number goes up to 13.5. And the 300mm telescope gets you down to 14.35 magnitude. That's seriously faint. Now, I have to be honest with you. Those numbers assume perfect dark skies and perfect quality telescopes. And most of us don't live under pristine Bortle Class 1 dark skies. So, in my blog, I've included a handy limiting magnitude calculator that also takes your sky conditions into account. You can choose your Bortle Class sky, and the tool adjusts the estimate accordingly. Under a city sky, you might only see a few dozen stars with the naked eye, but under pristine dark skies, you can see thousands. Now, keep in mind that the limiting magnitudes listed by telescope manufacturers are based on visual observations. But astrophotographers like me, we would like to attach a camera to a telescope and track the night sky with a telescope mount, allowing us to push that limit much further using long exposure photos. Unlike your eyes, which only work in real time, the camera sensor can collect light over minutes or even hours. So, how does this affect your limiting magnitude? To help you calculate your limiting magnitude for astrophotography, I've built an extra limiting magnitude calculator for you on my website. It gives a solid estimate of your limiting magnitude, which is based on the telescope's aperture, your sky conditions, but also the total exposure time. It's simpler to use than some of the most advanced calculators out there, and it makes some assumptions about your astrophotography gear, but it is relatively accurate and even a little bit conservative. For example, last month I shot 70 photos of 300 seconds each of the Whirlpool Galaxy from my Bortle Class 7 skies using my Edge HD 8-inch. When I inputted these numbers, my calculator gave me a limiting magnitude of about 20.2, but I checked the limiting magnitude of the stacked image in Astrophotography, which is software that can actually analyze stacked images and calculate your limiting magnitude, which was more than a magnitude deeper. Being somewhat of a nerd, I ran some extra tests in Astrophotography and the results were pretty interesting, so let me share them with you. This stacked but unedited image of the Whirlpool Galaxy with my Edge HD gave me a limiting magnitude of about 20.7, much closer to the 20.24 as predicted with my calculator. I also had Astrophotography analyze this 90-minute stacked photo of M51 I recently took with the C-Star S50 using its new 30-second EQ mode. It showed a limiting magnitude of about 17.9, so that's about 3 magnitudes less than the stacked image of the Edge HD. So, based on the brightness ratio, the Edge HD with its 200mm aperture should collect about 16 times more light than the C-Star S50's 50mm aperture, and that's actually the difference of 3 magnitudes, since 2.512 to the power 3 is about 16. So, based on these numbers, that brightness ratio holds up surprisingly well in practice. The aperture of your telescope also affects the resolving power. That's the ability to distinguish fine details in the night sky. This includes both the ability to separate two closely spaced objects like binary stars, as well as the power of resolving intricate details within single objects, like the cloud bands on Jupiter for instance, or details in a nebula. The resolving power is measured in terms of angular resolution. That's the smallest angle over which a telescope can separate details. But what does angular resolution even mean in the first place? So, okay, angular resolution has to do with how we actually measure the size of objects in the sky. The sky is essentially a giant sphere surrounding Earth, and we divide that sphere into 360 degrees, just like a circle. But because most celestial objects appear very small in the sky, astronomers use even finer angular units than degrees. So, for example, 1 degree is also 60 arc minutes, and 1 arc minute is also 60 arc seconds. So 1 degree is 3,600 arc seconds. Now, these angular measurements allow us to describe how large or close together objects appear regardless of their true size or distance. Right, so let's start with the full moon, which is about half a degree wide, which equals 30 arc minutes or 1800 arc seconds. When we move on to the Andromeda Galaxy, it's about 3 degrees across. That's a lot bigger, it's 6 times the moon's width. When we look at the Orion Nebula, it's 1 degree wide, so that's about 2 moons side by side. Jupiter is very tiny at about 30 to 50 arc seconds, depending on its distance from Earth. Equally, Mars ranges from just 4 to 25 arc seconds, and Venus is between 10 and 60 arc seconds. We can also look at double star systems like Albireo, and those two stars are actually separated by about 35 arc seconds. These sizes help you to illustrate what your telescope might resolve. For example, if your telescope has a resolving limit of about 1 arc second, it can theoretically separate 2 stars that are 1 arc second apart, or it may begin to show features on planets that span just a few arc seconds. So to estimate the resolving power of a telescope, astronomers often use Rayleigh criterion or Dawes limit, 2 formulas that give a theoretical resolution based on your telescope's aperture. These formulas actually assume perfect optics and excellent seeing conditions. Now, Rayleigh criterion is a bit more conservative and based on diffraction theory. It defines 2 objects as resolved when the central peak of one diffraction pattern overlaps the first minimum of the other. Dawes limit is a bit more optimistic and based on visual experiments with double star. It defines resolution as the ability to distinguish 2 close stars just before they merge into one. Now, on my website, I've included the calculator where you can input your telescope's aperture to instantly see the Rayleigh and Dawes resolution limits in arc seconds, which represents your telescope's smallest resolvable angle. Just keep in mind that real-world resolving power also depends heavily on the optical quality of your telescope and atmospheric seeing conditions on a particular night.
Let me show you some real-world images of Jupiter taken with a 100, 200 and 356mm telescope. So that's 4, 8 and 14 inches of aperture with Rayleigh limits shown on the right. Now I shot the first 2 images from my backyard and processed the last one using telescope live data. And you can clearly see how aperture impacts the resolution. The 14-inch reveals far more details than the 8-inch, and the 8-inch beats the 4-inch. So, while astronomical seeing and processing techniques matter, one thing has become very clear to me. Aperture is king, especially when it comes to planetary imaging.
I know I put a lot of info out there, so if you're still with me, thank you. I do have a couple of extra tips about aperture. First, when comparing apertures across different telescope types, it's important to keep in mind that some telescopes, like Newtonian telescopes and Schmidt-Cassegrain telescopes, have a secondary mirror that blocks some of the incoming light. This is actually called obstruction loss. For example, my Celestron Edge HD 8-inch has a 203mm aperture diameter, but it also has a secondary mirror with a diameter of 68mm. This means that the secondary mirror blocks about 33.5% of the aperture diameter, which might sound as a significant blocking of light. However, it is not as bad as it seems. If you paid attention in the beginning of the video, you know that it is not about the diameter, but the whole surface area. So we can calculate the obstruction loss by squaring the secondary mirror's diameter, that's 68mm squared, and divide that by the square of the total aperture, which is 203mm squared. Now, in this case, the obstruction loss by area is only about 12% of the total light gathering area. This means the telescope is still capturing most of the light, even though the secondary mirror is obstructing part of the incoming light path. If you're still here, thanks a lot, and as promised, I will give you some practical tips on when a larger aperture is worth it and when it might not be. As we've discussed, a larger aperture means more light and better resolution for faint objects in space, but before we all start dreaming of that 39-meter extremely large telescope in our backyard, let's discuss the trade-offs like weight, size, and cost. And let's start with APO lens-based refractor telescopes. For example, an 80mm Skywatcher Evo Star is very lightweight at 3.3 kilograms. It's about half a meter long and it costs about $700. But if we compare that to a 203mm SCAR APO refractor lens-based telescope, now we are talking about 18 kilograms. The telescope is over a meter long and it is priced at a whopping $9,000. And at this point, you really need to ask yourself, do you want to carry that outside every night? Do you even have a place to leave it set up? And do you have the money to afford that? Don't get me wrong, I think refractors are great, especially when you get started. And for instance, I love this little C-Star S50. But once you go beyond a certain aperture, like 130 to 150 millimeters of aperture, refractors are just becoming a bit too bulky and pricey for most people. Now, if you want more aperture at a more affordable price, you should consider mirror-based telescopes like Dobsonians or Newtonian telescopes. For example, an 8 to 10-inch Newtonian telescope will give you great light gathering power for about $500 to $1,000. The main trade-off here is that they are relatively large and heavy. So, for example, a 10-inch Newtonian weighs about 14 kilos and is over 1 meter long. So again, are you really going to carry that telescope around every night, or do you have a place to set it up? So if you're looking for a more compact option, definitely look into Schmidt-Cassegrain telescopes. These telescopes have folded optical paths that considerably reduce the size of the telescope. For example, I particularly love my Celestron Edge HD telescope. It's about 8 inches, so 200 millimeters of aperture. It only weighs 6.3 kilograms. It's under half a meter long, and it costs about $1,500. And you can use the Edge HD series also for astrophotography. So That's a pretty portable and powerful telescope, at least according to me. But I also have to be honest, if you move up to like an 11-inch Edge HD telescope, you're already looking at a 13-kilogram telescope and spending over $4,000. So at the end of the day, the best telescope is the one you actually use most. Okay, I hope this video taught you something interesting about Aperture. If it did, don't forget to like the video and subscribe to the channel. I'm Wido, and I wish you clear skies.